Hey, good morning. Today we'll continue with flip-flops. And before I proceed, does anyone have any questions on any of the material we have done so far? I think we rushed through the flip-flop timing diagram a bit. I want to make sure everybody understands this before I proceed. All good? Okay. All right, then let's take a look at the next one, which is the clocked SR flip-flop. Okay, clock flip-flop. So as I stated earlier, when we have sequential logic circuits, we use a signal or a waveform that keeps everything in sync, right? And so now have an additional signal as an input that is known as the clock signal, okay? Simply referenced by the notation C. For a standard SR flip-flop that is implemented, remember, SR flip-flop was simply two NOR gates tied together. We add two more gates, the front, tie to one of the inputs together, and we call it the clock signal. Okay, clock signal is simply a square waveform, which is on for a certain portion of time and off for another portion of time. Okay, it's a rectangular waveform with a 50% duty cycle. And this is the NOR, so standard SR flip-flop. Clock signal makes it so that until and unless a clock pulse is high, meaning 1, the flip-flop will not work. Okay, when the clock signal is 0, it doesn't matter what your input is. Your output is not going to change from its previous state. And we can very easily visualize this, because if the clock is 0, no matter what your R or S inputs are, the output of the AND gates are going to be 0. Okay, that's the most important point about this circuit. So when clock is equal to 0, output is 0, no matter what your input is. Sorry, not output. Output of AND gates. Output of the AND gates is 0, no matter what your input R and S are. And so if the AND gate inputs or AND gate outputs are 0, which is being fed into the SR flip-flop, now you go back and take a look at the truth table of the SR flip-flop. What do we have? When R and S are 0, 0, output is Qn minus 1, the previous state, meaning it has stored the output in memory. Output is not going to change. Okay. So again, an SR flip-flop with a clock, the clock must be high for the SR flip-flop to function. If the clock is 0, output of the AND gates is 0, meaning you are sending in 0, 0 to your NOR gates. When it's 0, 0, output Q remains in the previous state, Qn minus 1, which is here. Okay. When the clock is 1, then it functions as the SR flip-flop. Meaning if S is 1, then your output Qn is 1. If S is 0, output Qn is 0. Standard SR flip-flop. If clock is not present, If clock is not present and R and S is 0, 0, or sorry, if R and S are both 0, 0, then it doesn't matter what the clock does, because the AND gate output will always be 0. Okay. So when R and S are both 0, the AND gate outputs are always going to be 0. So then the clock signal becomes irrelevant. And the SR flip-flop output is again with the previous state, Qn minus 1, which is the first state in the truth table. Okay. So again, when the clock is 0, output remains in the previous state. When both R and S are 0, output is still in the previous state. Okay, the other outputs become irrelevant. And then as usual, if both inputs are high, meaning 1 and 1, that state is not allowed because we cannot predict the output. It's unpredictable. So we would ensure that our inputs would never go high at the same time. And that remains standard. The symbol for a clocked SR flip-flop was the standard symbol, box with an R and S, and you now have a third input in the center. Does this make sense? Let's take a pause. Let me know if you have any questions. All good? Okay, one more point before we go to the next slide. When the clock is present, it synchronizes everything. And so we say it's synchronous. When there's no clock in the circuit, we say it's asynchronous. Okay. Obviously, all modern devices that we use nowadays, laptops, desktops, any computing device, there is a clock present in there. CPU governed by a clock keeps everything in sync, right? CPU, memory address lines, storage, graphics processor, other processors, everything is kept in sync by that clock signal. Okay. Oftentimes, there is a need to set the output to either 0 or 1 before you begin your operation. So in that case, we add 2 more signals in there known as preset and clear. As the name suggests, preset meaning you are presetting your output to 1. And clear meaning your output is 0, clearing out everything. So preset means output is set to 1. Clear means output is set to 0. So in the previous slide, we saw the addition of a clock signal. Now you would see the addition of preset and clear signal. In the lab, when you're going to work with your ICs, there are logic gates, and each one of those may or may not have a clock signal. It may also have, may or may not have a preset and a clear signal. Okay, so a set and a clear signal. The preset requires the addition of a NOR gate at the output or the standard output of our SR flip-flop. So an OR gate. This is the NOR gate. This was our original SR or RS flip-flop. Okay. All right. Let's look at the operation of the preset and the clear. If preset is 1, output Q should go to 1. So if I write it here, if PR is equal to 1, then Q is equal to 1. And by extension, Q naught would be equal to 0. If clear is equal to 1, then Q is equal to 0 and Q naught is equal to 1. Okay. So let's see how that would work. If preset is 1, then the output of this OR gate would be irrespective of what is at the other input of that OR gate. Right? So if preset goes 1, it doesn't matter what is connected to the other input of that OR gate. 1 plus 0 gives you 1. 1 plus 1 will also give you 1. So preset goes high, output Q goes high. Same thing at the other end. If clear goes high, Q naught goes high. That Q naught is fed back into the NOR gate, right? So now I'm talking about clear. Excuse me. If clear goes high, right here, then output Q is high. Sorry, Q naught is high. Q naught is fed back into this NOR gate. If one input of a NOR gate goes 1 or goes high, what is the output of the NOR gate? Yeah, right. NOR gate is basically 0 plus 0 gives you 0, inverted 1. So both inputs of a NOR gate must be 0 for the output to be 1. For all other combinations, output is 0. So if this input, single input goes high, output goes to 0. If output goes to 0, and then preset would be 0, then Q would be 0 at the same time. Let me specify. If preset is 1, probably should have mentioned this. Both preset and clear are opposites of each other. So they would never be high or they would never be 1 at the same time. If preset is 1, by extension, it means clear is equal to 0. And if clear is 1, then preset is equal to 0. There would not be any condition where both would be high at the same time. Okay. So let me wipe that out and begin again. Okay. Clear is 1, preset is 0. If clear is 1, then our output Q should end up being cleared, meaning should be equal to 0. All right. So if clear is 1, then Q naught is 1. If Q naught is 1, that goes into the NOR gate. The output of the NOR gate goes to 0. And then the output of the OR gate, Q, would be equal to 0. Clear goes high, Q naught goes high. Q naught is fed into the NOR gate. So the output of the NOR gate goes low. If the output of the NOR gate goes low, then the output of the OR gate right here at the top would go low because preset would be 0 at that point. Let's take a pause. Wrap your mind through the circuit and let me know if you have any questions. Does the process make sense? Let's look at what happens when preset goes to high. Right? When preset is high, we would expect the output Q to be set to high, set to 1. When preset is 1, clear must be 0. So let's start the OR gate at the top. Output would be 1 because the input preset to the OR gate is 1. That is fed back into this NOR gate. This goes to 1. If a single input of a NOR gate goes high, then the output of that NOR gate goes to 0. That 0 combined with the clear input of 0 gives you an output of 0. And hence, preset equal to 1, Q is equal to 1. If clear is equal to 1, then Q is equal to 0. Okay. And so that is worn out right here. Okay. Actually, I should just mark this. Clear goes to 1, then output goes to 0. Output is cleared. Okay. Output is cleared. Hence the name of the terminal, CL or CLR, clear. And if preset is high or preset is active, then output goes high. Okay. The rest of the time, it behaves similar to a clocked SR flip-flop, meaning the previous flip-flop that we just saw in the previous slide. And the state of 1 and 1 is still not permitted. And there is no resolution to the 1 and 1. It's a race. It's a race to the output. Output would be unpredictable. All right, any questions? Okay. So the point of these circuits were to introduce students to the three different signals or 3 different terminals, which is the clock, the set or the preset, and then clear. Most logic gates will have all 3. Okay, most logic circuits will have all 3. So clock, preset, and clear. The clock signal was implemented with the use of a AND gate, and the preset and clear implemented with OR gates, summation. All right. So now we looked at the clock signal, right? Clock signal was shown right here. Okay, this was the clock signal. And depending on the frequency of the clock, there's a width that is associated with the on and the off pulse. Okay. right? We saw the on and the off cycle. There's a width associated with it. No matter how small that width is, it is still a significant significant amount of time. Whether it's in milliseconds or microseconds or nanoseconds, it still has a certain value. And in that portion of time, the output could become unpredictable. The output of a circuit could become unpredictable. And so what was developed was the edge trigger circuit, meaning the circuits would not respond to just the high or the low level of a clock signal, but instead they would respond to a rising or a falling edge. The rising and the falling edge correspond to when the signal goes from a lower value to a higher value, and the falling edge corresponds to where it goes from a higher value and falls to a lower value. So this is when the value is going up. This is when the value is going down, right? And it's basically the edge of the waveform, hence rising edge and falling edge. The other words associated with this is leading and trailing or lagging. Okay. The rising edge, falling edge, leading edge, lagging edge, trailing edge. These are all words that you may come across. Okay. But rising edge indicates a positive going transition, meaning going from a lower value to a higher value, and negative edge or falling edge would be going from a higher value to a lower value. So when it transitions, there is no ambiguity on how long a signal is on or off, right? It's transitioning. And hence it's known as an edge triggered circuit or an edge triggered flip-flop circuit. Okay. All right, let's take a pause. Let me know if you have any questions. Well, let's look at something known as the D flip-flop. Now you're not working with gates anymore, we're simply just D flip-flop. The D stands for delay. It could store data. It can store data. So if you look at the symbol, the flip-flop is just a square box, right? And the input signal on the left notes what kind of flip-flop it is. So this one is a D flip-flop. Output is Q, and then you have Q naught. C stands for clock. And this notes that it's edge triggered. It's an edge triggered flip-flop. Okay, it's an edge triggered flip-flop. The name comes from a knife's edge, hence an edge triggered flip-flop. Actually, Guess I can do a better job on this side. And then by the same, this is a positive edge triggered. Anyone want to guess or know how we can note a negative edge trigger? If you had your lab this week, has anyone had your lab on Monday, Tuesday, anyone? You place a bubble outside it. If it's a bubble outside it, it's a negative edge trigger, meaning a falling edge triggered. Positive edge, there's no bubble. So let's, the bubble indicates negative. And again, you will see this when you're in the lab and you're looking at the pinout diagrams of those chips, the shift registers and the logic gates. There'll be bubbles on some of them. If you have a bubble on the input or the output, it means it's negative edge triggered. Okay, so be very careful when you're building your circuits. And instructors will point it out to you in the lab itself. But again, this is something, as an engineer, this is something you should become familiar with. Okay. Even as a non-EE major, you would come across this. So if you see a bubble, it means negative edge trigger. Okay, so delay flip-flop, what does it do? Well, it simply, as the name suggests, it simply provides a delay. Whatever you provide as the input is sent to the output after a certain delay. So if Q is equal to 0, your output is 0. If Q is equal to 1, your output is 1. Okay. The important thing about this is it stores memory and it functions basically based on the clock input. Okay. So if your clock is 0, it doesn't matter what you give as the input, your output remains in the previous state. If your clock is 1, it still doesn't matter what the input is. Why? Because of this right here. It's an edge triggered, meaning, and it's a positive edge triggered, meaning it'll only work or only function when the positive excuse me, when a positive transition occurs in the clock input. So when the clock goes rising edge, then whatever is present at the input, meaning at the D terminal, is sent to the output. If it's 0, you get 0 at the output. If it's 1, you get 1 at the output. So the clock level does not matter. Whether the clock is 0 or 1 does not matter. It must have a rising edge. Then it will function. All right. Questions? Okay. All right. Qn minus 1. What happens when it's negative edge trigger? What does it do? Does it do anything? Doesn't do anything. So it doesn't matter. Output will remain Qn minus 1. Previous state. So it stores the data in memory. Okay, it stores the data in memory. So let's look at an example. Let's say we have a positive edge triggered D flip-flop. Okay, positive edge triggered D flip-flop. And we are given the timing diagram for the clock and the D input. Okay, positive edge triggered D flip-flop. So then what is the output? So this is the clock input. This is the D or the delay input. And this is the Q output. In the previous timing diagram, we identified the areas where the clock was 1 or 0. Here, we are told that the D flip-flop is a positive edge triggered flip-flop. So we need to identify all the areas where a positive transition occurs. Okay, so positive transition occurs right here. Okay, positive transition occurs right there. So 1, 2, 3, 4. Yep. If it was negative edge, we would have, so let's see, let's identify. Positive edge is 1, 2, 3, 4. So those are at 4 markers, 4, 8, 12, and 16. Okay, 4, 8, 12, and 16. Negative edge. Negative edges occur at 2, 6, 10, and 14. One, two, three, 4. Yep. That one. Make sense? Right? We are told that we have a positive edge triggered D flip-flop, so we identify all the positive edges. The 4 of them occur at 4, 8, 12, and 16. That is the only point in the timing diagram, or the only moment in the circuit where the output will change, or the D input is sent to the output. Okay. So then the next step is to identify the values for D. We got 0, 0, 1, 1, 1, 0, 0, and then 1, 1, 9 to 10, 10 to 11, 11 to 12, 12 to 13. 4 ones. 2, 4, 5, 6, 7. There should be 4 here. So basically superimpose the clock on the input, and then that would be our output. Okay, so let's see. Rising edge, we are not given any information between 2 and 4, right? Previous state. So previous state, don't know as it is. Okay. The first rising edge is at 4. What is the value of D at time 4? 1. The output goes to 1. Okay. Then it stays at 1. The next rising edge is at 8.
Is right here. What is the value of D when the time is 8? Then it must come down. Yes. Next rising edge is at 12. At 12, the value of D is 1. So then 12 again. The parts are good. And then the next rising edge is at 16. 16, the value of D is 0. Output comes back down to 0. That's total output. And after 16, we have to stay at 0. Okay. That's how you superimpose both the input signals, plot over the D. Then that might be out. Let's take a pause before it. Then if you have any questions. Yes.
Is the Q output at the start being 0 something would be given, or is that, or do we just assume that?
So we assume. So question being asked is, what about here? Falling edge, right? So we don't know. It should be Qn minus 1. The point being, from the information that we're given, we don't know. This would be unknown in this. It will simply be Qn minus 1. If it's given in the problem statement that a flip-flop is, the output is high. Currently, its output is 1. Or if it's given output is 0, then you can write in there. Otherwise, just make an assumption. Write Qn minus 1. Unknown. You can do the same example. Negative edge trigger. What the output looks like, and you can compare it. You already marked out. Okay. Any other questions? All right. So then let's look at what happens when the inputs are both high. We get what is known as a JK flip-flop. JK. And look, what do we have here? We have an edge trigger. Importantly, it's a negative edge trigger flip-flop. So JK is basically similar to a SR flip-flop, but it provides a resolution for the unpredictable state of both inputs being 1. Okay. So when the clock is 0, output does not change. When the clock is 1, the output does not change. It means Qn minus 1. Right? In this state, if it's holding on to the previous output, we say it has memory. It's just storing, has some memory, storing information. The clock arrives and it has a falling edge, then it functions as a SR flip-flop. J and K correspond to SR, right, actually it corresponds to no, it corresponds to SR, yes. J corresponds to S, K corresponds to R. So when J is 0, output is 0. When J is 1, output is 1. JK corresponds to S and R. Now, what happens? Both inputs are 1. And both inputs are 1, and the clock arrives, the output toggles. Okay. If the output was 1, it toggles to 0. If the output was 0, it toggles to 1. So the unpredictable state where JK is equal to 1 and 1. Output toggles. N minus 1 was 0. Then Q goes to 1. If Qn minus 1 was 1. Q goes to 0. So previous state was 0, output goes to 1, and the previous state was 1, output goes to 0. And there is a new name for that kind of flip-flop. Toggle flip-flop or T. The toggle flip-flop, both inputs J and K, both inputs are connected together. They're connected together, they're tied together to 1. The functions of the toggle flip-flop. Whenever the clock signal arrives, the output just keeps toggling 0, 1, 0, 1, 0. And you will see an application. It's a very important application of these kind of flip-flops. All right, any questions? Since I was talking about that, let me just jump ahead. We'll leave that for next class, but let me just jump ahead and show you the application. So use as a counter circuit. You have JK flip-flops. You tie the inputs together and connect it to logic 1. And then each flip-flop functions as a toggle flip-flop. And the output of each flip-flop goes as clock of the next one. Okay. So again, this is jumping ahead a little bit. But that's how a digital counter is implemented by using the flip-flop. You take the flip-flop, tie the inputs to 1. And once you tie it to 1, let's see how much time do we have. 12, 54, 55. Okay. Actually, we have enough time to go through this. All right, so let me begin again. J and K inputs are both connected to 1. Hence, we obtain a toggle or a T flip-flop. The T flip-flop output simply toggles between 0 and 1. Okay. The output of each flip-flop is fed as clock signal to the next one. Okay, it's right here. Q0 is going as clock input to the second one, and Q1 is going as clock to the next one. Okay, so reading from the left to right, I can say this is flip-flop 0. This flip-flop 1, flip-flop 2. In the binary number system, I would read the output in this direction. So you would write it as Q2, Q1, and Q0. If you apply as input a standard clock cycle, this is a negative edge trigger clock, all three of them. Then each successive flip-flop, meaning 1, 2, you can have a fourth one in there, 3, fifth one, always start with 0, right? 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is a 3-bit counter, 3-bit counter circuit. Okay, you have a JK flip-flop working in a toggle mode. The output of each flip-flop is fed as clock input to the next flip-flop. Okay, the first one would correspond to the least significant bit. So the first flip-flop, which accepts the clock input, the external clock input, will function as the least significant bit. And the last one would function as the most significant bit. So in a 2-bit counter, you only have flip-flop 0 and flip-flop 1. Output would simply be Q0 and Q1. In a 3-bit counter, as shown in this diagram, you would have 3 flip-flops, 0, 1, and 2, and outputs would be Q0, Q1, and Q2. And let's use a timing diagram to show how this would function. Keep in mind, all 3 of them are negative edge trigger. Okay, negative edge trigger. So if this is your clock input to the first one, clock input for flip-flop 0, let's mark out negative edge trigger for all of them. Right, these are the negative edge triggers for the clock input. Q0, let's assume all of them were at 0, 0, 0, right? So 0, 0, 0 at the beginning. It's a reset to 0. You're starting to count up. Negative edge trigger, output toggles to 1. That's flip-flop 0. Again, this is FF0, FF1, FF2. Output will be read as Q2, Q1, and Q0. So first state is 0, 0, 0. When the next clock cycle arrives, the negative edge doesn't arrive until this point right here. So output remains high until the next negative edge trigger arrives. When the next negative edge arrives, output toggles and goes to 0. Okay, that output is going to stay at 0 until the third negative edge arrives. The third negative edge arrives here, output toggles to 1. And so on and so forth for FF0. Right? But Q0 is fed as clock flip-flop 1. Let's count that as clock 1. And the negative edge doesn't arrive until here. So output of FF1 stays at 0 until the first negative edge arrives right here, when it goes to 1. It stays at 1 until the next negative edge arrives, then it goes to 0. the output of flip-flop 1 is fed as clock to flip-flop 2. We have time to let's finish this up right here. This doesn't change until this negative edge arrives, and this totals to 1. So if you read this in the reverse order, you get a 3-bit counter that goes 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, I mean 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. You have to read it in this direction. Q2, Q1, and Q0. Okay. So consider that as reading or review of set of class and class here today. See you all on Friday. This is also known as a ripple counter because the effects of the clock ripple through each flip-flop to the next. Okay. Also known as the ripple counter.
So what do you mean by reading from the bottom up? What do you mean by reading from the bottom up?
Reading from the bottom up means you're reading Q2 as the most significant bit. So you're reading it this direction. Q2, Q1, and Q0. That's how we will build our Q2. The way to now for 1, 1, 1, the clock resets 0, 0, 0.
So at 0.7, would it be 1, 1, 1?
Yes. 7 is the 8th state because it starts at 0.
Sure, okay.
So binary or logic circuits will always start at 0. So it will always end with an odd number.
And then the
A
sixth state,
2-bit counter would end at 3. 3 would be the 4th state. So 0, 1, 2, 3. A 1-bit counter would simply end at 1. So 0 and then 1.
Okay.
2-bit counter would end at 3, which is the 4th state. 0, 1, 2, 3.
Yeah.
3-bit counter would end at 7, which is 0, 1, 2, 3, 4, 5, 6, 7.
we always have one more state then. No. So at state 6, there would be 1, 1, 0.
Yes.